Astro Geeks? It is your host, Ophiuchi, and welcome back to the Ephemeris podcast. As you can probably tell by my voice, I've caught like an illness over the week. It's quite mild though. It's just, kind of irritating my throat and my nose. So yeah, that will not be preventing me from recording today's episode. And today's episode is about a special kind of nova, and that is recurrent nova. Obviously, for us to be able to discuss recurrent nova, we must be familiar with classical nova. So let's discuss that real quick. Classical nova are single eruptions of a cataclysmic variable. And what a cataclysmic variable means is it's a binary system of stars where there's a white dwarf and a main sequence star, or like something that's very similar to the sun in terms of stellar evolution. Or any star that's kind of within that category, or fits. So why exactly do these cataclysmic variables erupt and create classical novas? Well, the white dwarf steals hydrogen from the primary star of the system, and it forms its own accretion disk. And as this accretion disk gets bigger, there's more pressure and heat on the bottom of the disk. The pressure that we call, we call the pressure that the white dwarf gets from this electron degeneracy pressure, because that's the pressure that supports a white dwarf. And so the pressure and the heat on the bottom of the disk starts a nuclear reaction and a vicious cycle of hydrogen burning. And the nuclear reactions are generating heat, so they're fusing hydrogen to heavier elements. But then the heat increases the rate of the nuclear reaction, so it goes around full circle. And the electron degeneracy pressure keeps the newly created material from going anywhere, so that just kind of builds up until you get a big explosion and a classical nova. So some more about that. The stellar mass that's ejected away from the white dwarf in this explosion, they typically have speeds of around 1,500 kilometers per second on average, which is like 0.5% of the speed of light. And while that might not sound surprising, you really gotta think about it. Like, the fastest speed recorded by a bullet train is about like 600 kilometers per hour. So that translates to like 167 meters per second, which means that like the mass ejected from a nova travels 9,000 times faster than a bullet train at its fastest, which is crazy because when you look at a bullet train pass you by, your head just goes from left to right in an instant. So to imagine like seeing something travel at 1,500 kilometers per second, you'd imagine you get whiplash. That is fast. And if bullet trains aren't quite fast enough for you, the official speed record of a Blackbird, which is a really, really fast plane, is around 3,332 kilometers per hour. So that's about 925 meters per second. So that's only like reaching in on 1 kilometer per second. And so then if you do the calculations, the mass ejected from a nova travels about 1,600 times faster than a Blackbird at its fastest, which is, again, that's really crazy because like if you were to instantly accelerate to the speed of 925 meters per second, you'd pass out. So to imagine that there's something beyond that, like 1,500 kilometers per second, is insane. So, anyways, we were talking about classical novas. Sorry, I got really caught up in those numbers again. So classical nova are different from supernova because supernova is kind of like, it's basically a star explosion. So it involves the whole star kind of coming to the end of its life. It literally explodes. But with classical nova, a lot of the explosion transpires outside of a white dwarf. So there's that difference. And all right, let's get into recurrent nova because obviously that is the topic of discussion for today. So recurrent nova are nova that occur more than once, which I mean is pretty obvious by the name. They occur in shorter and dimmer bursts than classical nova, and they aren't quite cataclysmic variables. They're actually a little bit more specific. They're symbiotic binaries, and What that essentially means is it's a red giant in a dwarf star rather than like a normal star in a dwarf star. So let's be a little bit more specific about that. Cataclysmic variables is like the white dwarf is close enough to the primary star where its gravity just sucks the material. If you look at diagrams of a CV, you'll typically see a thin line uh, of just material that's getting pulled by the white dwarf. But with symbiotic binaries, the material uh, pulled by the white dwarf is from the Roche Lobe overflow of the red giant. And so let's talk a little bit about Roche Lobe stars. So Roche Lobe stars basically have a teardrop shape, if you can imagine that. And the Roche Lobe is just kind of the bottom of the teardrop. Just lots of stellar mass that's still like gravitationally bound to a red giant. And so what the Roche Lobe overflow essentially means is that it's the mass that escapes the bottom of the teardrop and the gravitational pull of the red giant and kind of goes to the white dwarf. So these differences aren't quite enough to explain the frequency of recurrent nova, apparently, from some of the information that I found online. So the proposed idea is that white dwarfs in the symbiotic binaries come very close to the Chandrasekhar limit, which pretty much just means that the white dwarfs in these systems are about as big as they can get without becoming unstable, and so they accrete way more matter. So that makes them unique enough to be a little bit different from classical nova. So, additionally, it's said that recurrent nova's white dwarfs are expected to increase in mass with each outburst. And they attribute this to the fact that in the thermonuclear reactions of a classical nova, the creation of heavier elements is detected, as I think we talked about. But in recurrent nova, it isn't. So they just assume that, okay, if it's not fusing hydrogen into heavier elements through these thermonuclear reactions, it must be, somehow adding to some of the mass of the white dwarf. So basically, shorter and dimmer bursts are a result of a difference in thermonuclear processes. Another additional thing is that recurrent nova are candidates for type 1a supernova progenitors, which is a term that gets used a lot in the studies, but let me just break that down for you. Basically, that's just a fancy way of saying the biggest and brightest supernova may have evolved from recurrent nova explosions. So, some other unique facts, only 10 of these nova have actually been identified in the cosmos, which is pretty crazy. Like, we've navigated close to 13 billion years of the universe, and we've only found 10 of these things across the whole thing. Like, that's pretty wild. But astronomers have a reason for this, and they hypothesize that it might be because most of the classical nova we see, we just haven't seen them erupt twice, which is the main, classifying factor for recurrent nova. If you forget all of the specifics and the details. But yeah, the most popular recurrent nova is RS Ophiuchi because it's quite easy for us to observe its outbursts, and it happens quite frequently. I think about once every 20 years or so. I don't know. Don't fact check me on that. Or yeah, don't take my word for it. Is what I meant. The most recent outburst of RS Ophiuchi was in 2021 with a max increase magnitude of about 5. A lot of, I think on average, recurrent nova typically increase by about like 9 magnitude, whereas classical nova, they brighten by about 12. So, yeah, if you think about the magnitude scale, like 5 is quite a big number, 12 is even bigger. That's wild to go from, yeah, for 12 magnitude difference, that gets really, really bright. But yeah, that is all I have for today's episode. I do want to talk a little bit about the trajectory of the podcast. I don't know if I did this very recently or not. I think this is going to be not a whole lot of new information, but we're probably going to do a couple more of the fundamental astronomy episodes for what I'm going to call season 1. And then I think there's going to be a period in the podcast where we transition a little bit more into cosmology. For the plans that I have now, season 2 is probably going to be really, really short, but I'm hoping to expand the season 2 by bringing in more ideas for what we can talk about in terms of cosmology. And then I think season 3 is going to be a mishmash, kind of looking into more recent discoveries, because that is kind of the end goal for now in terms of where I want to go. Like, really cover some basics, cover some theory, and then get into a lot of the new stuff, because I think that's what's quite exciting about any field of science. I don't expect to need to go into season 4 or more in the near future, but if such a season does come, it might be because there's a major change to the podcast style. Like, I don't know, maybe like we get experts on the podcast, you know, wallahi. But yeah, so that's kind of the framework that I've laid out for the podcast. It is definitely subject to change, because I might like change my mind once or twice here and there. But yeah, if you enjoyed listening to the podcast today, make sure to follow me on Spotify. If you're listening from YouTube, make sure to subscribe to the YouTube and also visit Spotify. And yeah, I will catch you guys in the next episode. Peace.